Mr. Matt Wallace, the Flight Systems Manager for the Mars Science Laboratory Project, has accepted our guest lecture, and let me give you a little bit of a background from him. Matt Wallace graduated with distinction from the U.S. Naval Academy, class of 1984, and served in the U.S. Submarine Fast Attack Fleet. He obtained a master's degree in electrical engineering at the California Institute of Technology, Caltech, and joined NASA at the Jet Propulsion Laboratory in Pasadena, California in 1991. So that's 21 years, huh? He has held leadership positions on various robotic planetary missions, including 3 Mars rover missions. He managed the assembly, test, and launch operations team for the Spirit and Opportunity rovers, and led surface missions operations for the Opportunity rover after it landed on Mars in 2004. Over the last 7 years, Matt served as the Flight Systems Manager for the Mars Science Laboratory Project, overseeing the development of the spacecraft systems for the next Mars rover, Curiosity, that it successfully landed on August 5th, 2012. With no further ado, Matt, thank you very much for being here.
Happy to be here.
Let's make sure your mic works.
You guys hear me?
Quick test.
All right, so Mars. A lot of times I start off trying to answer the question, why Mars? You know, because we get that a lot. Why are we interested in the planet at all? And one of the things people don't realize is Mars is very much a sister planet to the Earth. In fact, it unlike some of those large outer solar system planets like Venus and Saturn and Neptune and things like that. I'm sorry, like Venus, like Saturn and Neptune and Uranus and those sorts of planets. It's not a large gas planet. It's a rocky planet, much like the Earth. And it has a pretty similar history. And in fact, it has a year that's reasonably similar to the year we experience here on Earth. It has seasons as it goes around the sun. It's tilted at about the same angle as the Earth, actually, which makes its season reasonably similar. So you see polar ice caps freezing and then melting, and much like we do here on Earth. It has a diurnal cycle. It spins on its axis. It actually spins at about 24 hours and 40 minutes, very close to the day on Mars is pretty close to the day on the Earth. And it's of interest to the science community because we think at one time, in fact, it was a lot more like the Earth. And so the question is, for many folks, is what happened? But in the mid-1990s, people started looking at this rock over here. This is called Allen Hills 84001. As you can see, it was a meteorite that was picked up in the Antarctic in 1984. And as they looked at the rock, as you might be able to see in this top left-hand pictures, they saw some structures that they found curious. And so as the science community started to take a closer look at them, they started to wonder if, in fact, what they were seeing was evidence of ancient microbial life in this rock that was determined to be a meteorite from Mars. And so that kind of sparked a new interest in the planet. It, you know, kind of went to one of the fundamental questions that we all wonder about. Is Earth the only place where life has evolved? And if we can answer that about a planet next to our own, it certainly has implications for the rest of the solar system and the universe, right? And so as those sorts of questions started to bubble around, the agency, and the space agency, started to put together a program to kind of attack that question. And over the course of about a decade, there's been a series of different Mars missions, a number of which I worked on. The first one was this mission. It was called Mars Pathfinder. It launched in 1996 and landed in 1997. It carried the first rover, actually, that rover in the top right corner up there. Was called Sojourner. It weighed about 25 pounds. It wasn't very big, the size of I always say the size of a bread box, but nobody has bread boxes anymore. So size of a microwave oven, right? And it was really meant to be a demonstration. It was the first autonomous rover we've ever landed on a planet. And the idea was to understand what that sort of mobility and what a rover could do for us from a science perspective. And more importantly, you see the big airbags on the top. The mission was designed to prove, in fact, that we knew how to land on Mars with these relatively low-cost landing systems. And so for the first time, we actually touched down on Mars, cocooned inside these large airbags. Those airbags were about 2 stories high, actually. And after we landed, we rolled for about a mile or a mile and a half or so. We eventually stopped. We pulled the airbags, deflated the airbags, pulled them in, opened up the lander. This is a picture of the lander. The picture was taken from the rover. And then drove the rover down this ramp and onto the surface. The mission lasted about 3 months or so. But it carried very little science. It was really just designed as an engineering experiment. So on the order of about 11 pounds, maybe 5 kilograms or so of science instrumentation. That was about all that could be carried. So the next mission said, hey, you know what? Let's try to make this a little more capable, try to start answering some of these fundamental scientific questions. And Spirit and Opportunity, which are the 2 larger rovers sitting behind this Sojourner engineering model down here, were born. And I worked on that program as well. I started in 2001, and the 2 vehicles were launched in 2004 to opposite sides of the planet, one to a place called Gusev and one to a place called Meridiani. And this is a picture after the rover has, they as well used the airbag system that was proven on Mars Pathfinder. And this is a picture of the Opportunity lander looking down into the crater that we had rolled into. The crater was called Eagle Crater. It's a relatively small crater. And the rover was able to drive off and start exploration soon thereafter. And these 2 missions have been very successful. They were designed to last 3 months. Spirit lasted about 6 years before we finally lost it. And Opportunity is actually still operating today, almost 8 years after it landed on Mars. So the 2 vehicles have been very hardy, and they've done a lot of great science. So the objective of the science for Spirit and Opportunity was to follow the water. In other words, it turns out for life on Earth, you need 3 things. You need energy, you need liquid water, and you need organics. So we know that Mars, much like Earth, has an energy source. It has a sun, right? And the surface of Mars obviously is exposed to the sun. And so there's an energy source on the surface. What it doesn't have currently is liquid water on the surface. And so the objective of the mission was to explore these 2 areas that the 2 vehicles landed at and look for evidence of surface water sometime in the geological history of the planet. And what the vehicles found as they looked more closely at some of the rocks at the landing sites, particularly Opportunity at Meridiani, was some patterning and some layering that you can see over here on some of these rocks that were indicative of an aqueous solution. In other words, they were laid down in they're sedimentary rocks, and they were laid down in some sort of shallow lake bed, was the conclusion. That was reinforced by finding these little things, which the engineers called blueberries, because they looked like blueberries in some of the pictures. But in fact, what they were small accretions called made out of a compound called hematite, which is an iron compound. And that compound only forms in the presence of water. And so we had now multiple indications that, in fact, at the landing sites that we were at, that there had once been, somewhere in the history of Mars, surface water, perhaps, something that looked along the lines of this particular lake on Earth. So we had 2 out of the 3 elements of life at this point. We knew we had energy arriving on the surface. We knew we had evidence of past surface water. And so the next question was organics. Life just does not exist without organics, both in its from a habitability perspective and from a post-life signature perspective. There's organics. That's what we're made of. That's one of the things that define us. And so the next mission was specifically designed to look for evidence of organic signatures. But to look at organics, you need a tremendously complex science suite. And so we couldn't launch another rover the size of Spirit and Opportunity. They were about 350 pounds or so, each one of them. We needed a rover that was much, much bigger. In fact, car size. And that was the birth of Curiosity. Curiosity weighs in at about 1 ton. It's about the size of a Mini Cooper. And it carries a suite of 10 different instruments. You may have remembered I talked about only about 5 kilograms of science on some of these previous missions, 11 pounds or so. We carry almost 200 pounds of science instruments. And if you include the robot arm and the mast and the drill and the other things that are used by the science payload, we're pushing over 500 pounds worth of science equipment on a vehicle. So that's great. You know, we came up with the concept of a very large vehicle. And here you see another shot of the vehicle with its robot arm straight up. The top of the robot arm is about 10 feet off the deck. So if you can imagine this thing dunking a basketball, you get a sense of the size of the vehicle. Here we're doing some testing on a tilt platform. The vehicle is designed to actually rotate or to be able to drive up and down slopes that are about 20 to 30 degrees actually in inclination. And so that's one of the tests that we were doing here. But it gives you a sense of just how big the vehicle was. So that's great. So we have a big vehicle. It's got a lot of science capability. It's what the science community needs to take the next step in exploring Mars. And so the problem being, we don't know how to land a mission of this size. The airbags would be 3 times the size of this building to land something that was 1 ton. It was just not practical to use the same landing system. And so the challenge became finding a landing system that was compatible with a 1-ton rover. And that's where Skycrane, which is a landing system, came in that we used for the Mars Science Laboratory to land the Curiosity rover. This is what it looks like as it gets towards the surface of Mars. The rover is actually, you can see the wheels, they're folded up sort of underneath the bottom of this delivery system, which we call the descent stage. The descent stage has a bunch of propulsion systems on it and inertial measurement units and electronics and power systems and all those types of things. And it essentially is the jetpack, if you will, that carries the rover down to the surface. But we can't land the whole thing. That's much too much mass. The rover just simply couldn't tolerate that much mass on the structures and systems. And so what we do is we separate the rover from the descent stage on about a 20-foot bridle as we're getting close to the surface. And we deploy the mobility system. We touch down the rover. And we cut the bridle and we fly it away. That was the idea. That was the concept we came up with. And as I said, we call it Skycrane. And after we touch down the rover, we cut the descent stage away, it flies off. And we like to use the word impacts, which is just a nicer way of saying crashes into the ground. So here were some of the early touchdown tests. Again, we talked to, this is a picture of the rover dropping onto the surface. We don't play it in just a second. But I'll point out, this doesn't look a lot like Curiosity, and that's on purpose, because it's only about 40% the weight of the actual vehicle. We didn't put a computer on it. We didn't put power systems on it. There's no brain, and so we called it the Scarecrow because it was no brain. And we dropped it, and we did some drop testing. Then eventually, there's some follow-on video here that shows some higher fidelity rovers getting dropped on some more aggressive surfaces. So here it is coming down. Let's see if I can get audio here. There we go. There's a higher fidelity vehicle, what we call our dynamic test vehicle. You can see we've dug a trench and we're dropping it on about a 20-degree slope, and you can see it knocking over some rocks and things like that. Again, pretty complicated test, but necessary. So once we came off the launch vehicle, it took about 7 months to 8 months to get to Mars, and the question, of course, is if you're going to Mars, where do you go? What's the best place to go to try to figure out what you're, try to find the types of things that you're looking for? And the science community, for the most part, want to go to places that have vertical relief. In other words, stratigraphy, a crater wall where you can look at Grand Canyon, right? You guys been to the Grand Canyon. You can look down the walls of the Grand Canyon. You can see, years and decades and thousands of years, millennia of different, of history, essentially, in the geography on the wall of a crater, right? Same thing is true for a mountain, right? As you go up or you go down a mountain, you see the changes in stratigraphy are essentially representative of the history of the planet geologically. And so we had a group of scientists, that said, hey, we want to go to a mountain like Marth on Mars. And then you had another group of scientists that said, hey, no, we want to go to a crater, like Gale Crater or something like that. And so we looked and we looked and we looked and we looked, and we found a crater with a mountain in the middle of it. And that made them very happy. This is Gale Crater, actually. The center of it is called Mount Sharp, which you can see there. And the sides of the crater are a little hard to see here, but it's essentially a circular crater with this mound or mountain in the middle. The mountain's pretty high. It's about 2/3 the height of Mount Everest, so it's a pretty high mountain. But the slopes are very gentle, and so the rover's actually able to climb up the mountain, as well as obviously have access to the crater walls. This is landing day. We have, at this point where the video picks up, we have arrived at Mars. We're traveling at about 13,000 miles an hour relative to Mars itself. And over the course of about 7 minutes from where we hit the outer atmosphere at that speed to where we touch down on the ground, the spacecraft has to go through an enormously complex set of operations, which we call entry, descent, and landing. It's all done autonomously. The light time between here and Mars is about 10 minutes. And as I said, it's only 6 minutes from the outer atmosphere to when you hit the surface. So this is all pre-programmed, all pre-tested. And in fact, when we get telemetry back from Mars saying we either successfully landed or we cratered, it had already been over for 10 minutes, right? And so it makes this part of the mission, this phase of the mission, particularly difficult. And so this is what happened on August 5th, the night of August 5th. Let's see if I can get this going. Let's see if we got it.
We should have parachute deploy around Mach 1.7.
Any audio? That's okay.
Parachute is deployed.
So I'll talk you through it. So we're, at this point, we're getting ready. We've deployed the parachute, as I said, at Mach 2. We've dropped the heat shield off. You can see the heat shield falling away. That's actually imagery taken from the spacecraft. We're still on the parachute. We dropped out of the parachute, the back shell, at about 100 miles an hour, and the jets fire up. This is the team watching the process. We're getting telemetry as we go. We're getting indications of what's happening. We're getting closer to the surface. We have a radar on board. It's telling us how close we are to the surface. We deploy the rover about 100 feet up, and we had a pretty large audience around the country, actually. Even Times Square, they were projecting it up above on the big TVs in Times Square. And that's the point at which we got the indication. And the Mars rover to the surface. Everybody's celebrating. And I think this then moves into some of the press conference. There's Times Square. It's actually pretty exciting. Some of the landing sites around the country. There's all of us in our blue shirts being very happy. The first image came back on the first night. There was a press conference at JPL, NASA administrator, congratulating the team, and John Holdren, the White House Science Advisor as well. Very exciting time. So it was a successful touchdown and a very exciting night. And then one of the first pictures taken from our hazard avoidance cameras up in the front of the vehicle, and you can see the shadow of the vehicle looking out towards that Mount Sharp in the center of Gale. This is one, once we get over there, actually we've already started this. This is one of the science experiments we carry called Chemcam, also known as our death laser. It's a pretty unique instrument, and I like to tell people about it because it's indicative of the type of ingenuity and the type of innovation that the science community and the agency encourages and is necessary to do some of these missions. But as you might imagine, as you're roving around Mars, you don't want to stop at every single rock. It just takes a long time to approach the rock, to deploy the robot arm, to get your instrument down, to collect the data, to get it back to Earth, to have it looked at, and so on and so forth. So what we want is what we call standoff capability, remote sensing. We want to be able to, without actually going over to a rock, to get some sense of what it's made out of. And that's what this instrument actually does. It fires a laser out of the top of the mast. The laser actually creates a sort of plasma cloud out of the material on the surface of the rock. And then there's a spectrometer that images that cloud and is able to determine at a fairly gross level what kind of elemental composition we're looking at for the rock. Okay, so the question, just to repeat it, was how far-reaching, how extensive is the science community for the project? Is it just U.S. or is it international and so forth? It's very much international. It's always been that way on all the missions I've worked on. The science community, I find, is semi-borderless, really. You know, they do a much better job than the engineering community, I would say, in staying coordinated across their respective space agencies and universities and areas of interest. We have 10 instruments on the vehicle, which is a lot of instruments. We have 3 of them. 2 of them are, in fact, contributed from other countries. We have one from Russia, which is a neutron generation instrument that generates high-energy neutrons. They're directed into the ground, and then there's a sensor that looks at the reflection of those neutrons. And it gives us an indication of whether or not there might be water or ice underneath the surface of the planet where we're at. So that's called the DAN instrument. That came from Russia. Let's see. The Spanish have contributed a weather station actually for the rover. It sits on the mast. It has wind sensors and pressure sensors and things like that. And so we have 2 out of 10 instruments are directly contributed. The laser, the death ray, you know, a large fraction of that was actually built in France. And then every instrument, pretty much, I bet you every single instrument has either an investigator or a co-investigator, a scientist assigned to its team that comes from other countries. So it's extremely broad, very far-reaching. They come from schools, they come from other NASA centers, they come from industry. James Cameron, you know, Titanic and what was the
Avatar.
Avatar, yeah, thank you. Right. He's a co-investigator on our imaging system. I got a chance to meet him. He's a pretty cool guy. So, you know, so it's very, very broad and very far-reaching.
Did NASA perform simulations or modeling to eliminate, reduce expensive tests?
Yes, we did. I'll give you an example of that, actually. Let me come back here a little bit. This might be a bad idea. Seems to be going slow. But the parachute is a good example of that. Let's see if I can get there. Parachutes as I said, they have to deploy at very high speeds. If you can imagine traveling at Mach 2, deploying this enormous parachute, 21.5-meter parachute, and carrying, thousands of pounds underneath it, and having to slow yourself down from that speed, down to something like 100 miles an hour. You can imagine parachutes are very, very challenging elements. They're very, very hard to test. Mars parachutes are very hard to test because the Martian atmosphere is only 1% the density of the Earth atmosphere. And so it's not like, we can test it in the wind tunnel to make sure, in fact, that it inflates and that it's stable and that there's strength and things like that. But there's a whole bunch of dynamic effects that you can't test in a wind tunnel. In a wind tunnel, I mean we have winds that are at tens of miles an hour, right? Entirely different from deploying this thing at supersonic speeds, right? And so historically, the only way to get a high fidelity test on a parachute is to put it on a sounding rocket or a very high altitude balloon and launch it on a rocket actually at extremely high altitudes where the atmospheric density is similar to that of Mars, and then deploy it. We're talking about tests that are tens, maybe hundreds of millions of dollars to perform. So over the last 30, 40 years, every parachute that we've used has actually referenced the original high-altitude parachute testing that we had done back in the late 60s and the 70s, called shape and PEP tests. Came MSL, Curiosity, even bigger chute, much bigger. And the question was, hey, shouldn't we go back up and do a high-altitude parachute test again? And after looking at it for a long period of time and collecting a lot of the parachute experts in the industry and so on and so forth, we came to the conclusion that we could, in fact, do this analytically. And the reason we could is because some of the CFD analysis tools now are just so extremely powerful that you can actually do soft goods modeling with computational powers that we couldn't even think of 5-10 years before now. And so that's an example of a place where we saved an awful lot of money by taking advantage of current state-of-the-art modeling and simulation. But we do it all the time. You simply can't simulate a full entry, descent, and landing system on Earth. And so we model that entire thing and do Monte Carlo analyses of the modeling. It's a very complex process and many, many years worth of work. And we do that pretty much everywhere, trying to save money. We also test a lot. We test, as I said, you saw a lot of tests. And maybe this is a good place to talk about testing. We have a policy, I guess, or a standard, a guideline in what we do that's called test as you fly. So when we begin to define our test program, we start with the assumption that we want to do every test that we can think of with as high a fidelity as we can possibly manage. And then we only back away from that when we get to a condition that we think is extreme. And that has proven over the years for these very aggressive, one-of-a-kind missions to be extremely important with respect to the reliability of the system. I'll show you an example of this. You saw some of those sky crane deployment tests and things like that. This is another test that we did. We actually hauled the flight descent stage in our high bay up to the ceiling. We put some absorber material around it. We kept the rover down here. We extended our bridle, which carries sensitive electronic signals from our IMU up on the descent stage. And we started radiating out of our antennas, our UHF antennas, our X-band antennas, to see whether or not that radiation, that electromagnetic radiation, would interfere with the signals on the cables. It's an example of, even though the analysis, for instance, said that we should be fine, we should have plenty of isolation, the signals should be robust, it's the type of thing that we do. We try to create a very high fidelity environment and test like we fly.
Jumping to the topic of project managers.
Sure.
Were project managers people with technical backgrounds, managerial backgrounds, or a combination of both?
Okay, so the question was, are the project managers folks with technical backgrounds, managerial backgrounds, or both? Rightly or wrongly, where we work, the managers tend to be folks that were very good engineers. That's how it works at the Jet Propulsion Laboratory. We don't hire a lot of people that just manage. Now, it's very hard to elevate up the management chain unless you have a lot of the management skills that you need to have to do these kinds of jobs, right? This is a $2.5 billion project, right? And you just don't become a manager of this type of a program without having good communication skills, you know, good understanding of organizational responsibilities, a good understanding of how to manage risk and how to manage schedules and costs, you know. And so I think we end up with folks that have both skill sets. But we start out hiring from within. And so we always at the core of pretty much every project manager or spacecraft manager like myself, you know, anybody working at that level, they almost all have, perhaps myself excluded, have enough project, you know, management skill sets that they have the ability to do both. They have good people skills, all those things that you need to be a good manager.
What's going on right now? So here are a couple of questions that our Facebook community has posted. And first one from Ashish Lodra. There you are. We've had a hard time crashing tasks for relatively simpler projects, right? So all of us have run projects in one way or another, trying to meet deadlines.
Yep.
You know, in many cases, how do you crash studying time so that you can know the stuff for the midterm or the final? I can't imagine how difficult it would have been to edit the duration of tasks for a big project such as Curiosity. So maybe you can talk a little bit about that.
About editing the
Crashing.
Oh, the compressing?
Duration. For example,
Yeah.
the critical path is too long over here.
Yeah.
How do you...
The techniques for compressing schedule and things like that. It's not at all unusual for us to get into a situation where some element is behind, and it is the linchpin in some follow-on type of activity. And so if we don't accelerate it, if we don't catch it up, we're going to slow everybody else down. We've become experts at dealing with these kinds of situations. And I'll try to genericize, I guess, some of this so to give you guys a sense of some of the techniques you guys may think about, right? You can always look at scope, right? You ask somebody to do a job, and you give them a set of requirements, and it's taking them longer than you expect them to do it, and you say, you know what, that's too hard. We're going to make it easier. We had problems with actuators, the mechanisms, the actuators that drive the mechanisms, the mast and the arm and things like that. And one of the things we were trying to do with the actuators was to make them capable of operating at these very, very cold temperatures, as well as lightweight them. So we were trying to make gearboxes, very complex gearboxes out of titanium, and use dry lubricant instead of usual, wet lubricant, because the wet lubricant was not tolerant to the very cold temperatures. And so we were trying and we were failing, and we were trying and we were failing, and they were getting farther behind, and we were getting worried, and we were getting more worried. And we finally got to the point where we said, you know what, we're just not getting there. We're going to change the requirements. We're going to put heaters on all these things, and we're going to use some of our precious electrical power to actually heat up the actuators before we use them. And we're going to go back to a wet lube system for most of the gearboxes, and go back to steel gears as well. We're going to just let them be heavier, and we're going to deal with that in the rest of the system. And we went through that cycle, and we started to make progress. That's one technique. You can change the job, right? Another way is to motivate people differently. When Let me ask you guys, what's the number one motivation for people out there in industry? Fear? Money. It's money. You know, if you want to accelerate something, you can incentivize them. And we do that frequently. It is a good lesson for you guys in communication, actually. It was not at all unusual for somebody to come and report to me, hey, this is falling behind, it's falling behind. We're just not going to make it, you're going to have to deal with it. It's going to be 2 months later, 4 months later, whatever. I said, well, why is it late? And they said, well, we're just not going to, our sub-vendor just can't assemble this thing. He said, well, what's your sub-vendor waiting for? Well, and you just keep drilling down, you're drilling down. It turns out he's waiting for a 10-cent capacitor, right? And if you incentivize that guy, you pay 20 cents instead of 10 cents for, I'm exaggerating, right? But I mean, maybe, instead it's a 1K part, and you pay 5K to incentivize these guys, and they work overtime, they work weekends, and they put you ahead of the job, that they're doing for some other company or whatever, and suddenly you're right back on track, right? And you've saved yourself hundreds of thousands or millions of dollars by saving a couple months because you spent, $5,000 or $2,000 to incentivize this one part. That's another way to accelerate schedule. There's also, instead of accelerating schedule, there's mitigation for late schedules, right? We do this frequently as well. The pictures I already showed you guys. This picture here. It turns out, to integrate the descent stage, which is that thing hanging up there, we need most of the rover system. Because the rover is where the brains actually sit, the computer sits there, and you can't electrically integrate, a lot of the electronics and power distribution and radars and things up on the descent stage without having a computer to interface it to, because the computer is the interface to the operators, the test operators and things like that. And the rover was late, right? It has all kinds of new stuff on it, new instruments and new actuators and new chassis, and I mean, it's an aggressive development, so it was running behind. And we were worried about the fact that, it was going to essentially get in series with the descent stage, and we wouldn't be able to make progress in our system integration and testing. And so what did we do? We went out, we got a non-flight computer, basically, and we took it down onto the floor, and we interfaced it via these bridles and some other cables and things like that up to the descent stage. And so we didn't have a rover, but we had what we called a surrogate rover, actually. And by using that technique, we were able to start integrating not only the descent stage, but all the cruise stage and the aeroshell systems as well. And we got way out ahead so that when all the late stuff came in down here, we could focus all our energy there. Another technique for dealing with things that are coming in late. Okay.
Again, this question actually came from Jose. What lessons learned did you have from the project, and what surprises were there, if any, regarding the lessons learned?
Well, in truth, there's an enormous number of lessons learned. I mean, you just can't do this much work without learning a lot about your processes, about your engineering designs, about your standards and things like that. We track these things, actually. When we have a problem, we write something called a problem failure report. I believe at last count we were at 3,600 problem failure reports on the system, and that's just at JPL. All our contractors and vendors and things like that, they have their own tracking systems. And so in many ways we track those things, and we identify the problem, and we close them out to the degree that we can. Many of these have not just proximate causes, but root causes. You really kind of have to dive down. Some technician over-torqued a screw. Okay, well, you write a problem failure report, you take the screw out, you put a new screw in, right? Well, that's fine. That's the proximate problem. But you have to understand the root problem. Why did he over-torque the screw? Was his training not good enough? Was the tool not calibrated appropriately? Was he too tired? Are we working people too hard? So think about having to go through that conversation 3,600 times. It's a pretty, we take these types of things very, very seriously. And then at the end of the project, we try to gather them up, actually, look for trends, look for places where we see problems that have common elements, and then identify process and standard changes again. Look at what we want to do the next time around, and incorporate those things. And there's a number of different agency and tools at the Jet Propulsion Lab that we use to track those and track the corrective action on them. What were some of the key lessons learned on MSL? I think for me, I'll speak for myself, one of the things that I learned was there's only so many new things that you should try to do. And MSL was really, curiosity was really at the breaking point for these missions. There was very little that we could carry forward from our previous missions. And so everything had not only expected problems, but it had unexpected problems. It had known problems and unknown problems, as we like to say, and unknown unknowns, because we had never done it before. And maybe that's perhaps the lesson. One of the things you guys ought to think about is when you get into these projects, ask yourself, how many new things are there here? How many things are really like something I've done before? And how many things are really new? And I'll tell you what happens if there's too many new things. They start to interact with one another. And it starts to become, rather than linear, it's a geometric problem, right? Or a cube problem or something. And that was part of the challenge we had on curiosity.
How do you decide / balance between allowing engineers to be creative and design new ideas versus allowing them to reinvent the wheel?
Yeah. How do you decide between allowing engineers to be creative as opposed to allowing them to reinvent the wheel?
Or stick to a schedule?
Yeah. It's always a balance. I may have I have a chart here to kind of illustrate some of that. We talked about schedule management. I talked a little bit about the fact that you have to understand and manage the number of new things that you have. We have something in the agency called technology readiness levels. You can see them up here, TRLs. And they're essentially measurements of how mature a particular concept is. This is, you start down at TRL 1 and you work your way up, to a point where you have analytical or experimental critical functions, or you have a component, breadboard, so on, all the way up to the point where you're actually testing a prototype in a relevant environment. That's kind of TRL 7-ish. That's about the point at which we allow new ideas, creative ideas, to actually get baselined into a project. When we started talking about this extremely large rover in 2000, we recognized that we had a problem. We needed some sort of innovation, and we didn't know how to drop it onto the surface. Somebody wrote this up. Somebody, as they were coming up with different ways of doing it, somebody made this little cartoon saying, "Hey, how about a stork, right?" And we looked at extremely large airbags. For instance, I talked about the fact that, they would, for a system this massive, they would have to be enormous. That didn't work, but we looked at it, right? We looked at landing on a pallet, and then putting the propulsion system underneath, and then driving off the pallet. That also had a number of different problems, which I'm not going to go into. We looked at landing on a rope, that with the coming off the back shell, that had problems because we didn't have the control authority that we needed from the solid rockets up in the back shell, and so we took this previous landing concepts and we combined it, as I said, with this heavy lift sky crane concept, which gave us some compliance. Actually, it allowed us to touch down and then actually sense the touchdown and know for sure that we had touchdown, and then cut the ropes and then fly away. We already were flying a mobility system that was designed to interact with the surface, and so this was an area where we needed innovation, and we developed that innovation.
How much of the rover was developed and built by JPL versus subcontractors, and how did you deal with subcontractors in the other countries? Like, were there a lot of political issues that you had to go through to be able to, bring things in from the other countries, or in the scientific community, is it at this level versus like military and stuff that we try to keep secret? Was it pretty fluid? Or were there a lot of roadblocks?
So how much was done? I don't know the numbers exactly, but I think somewhere in the order of 40%, 35-40% of the cost of the flight system was, the spacecraft system was subcontracted. And then we had a lot of work that was done, although we call it quote unquote in-house. We have a lot of work that in fact is at a lower level, subbed out to small machine shops and assembly, assembly companies, electronic board assembly companies, and things like that. And of course, we buy all of our electronic parts and a lot of our components as well. So the actual true fraction of money spent on people or on processes inside JPL versus outside JPL, I don't know, but it's probably, I gotta believe it's less than half, of the total spacecraft. We operate in multiple modes at JPL. All the NASA centers do. This particular mission was what we call an in-house mission. In other words, we did do a lot of work in-house. But it's not at all unusual for us to subcontract out the entire system contract to Lockheed Martin or to, some other aerospace company, and done that with Orbital and Northrop and a whole bunch of others. This particular one, we had a higher fraction in-house. How do we manage it? So most of the components and the hardware we buy, almost really all the subcontractor work we do is with U.S. companies. It's part of the government acquisition requirements sets and things like that. In addition to that, it is hard to work with companies overseas. There's something called ITAR, which some of you guys may have heard of before, International Trafficking in Arms Regulations, that do in fact protect these spacecraft technologies as potential military systems. And so we get a lot of scrutiny about the information that goes between ourselves and companies and organizations outside of the United States. And so for all those reasons, we do tend to do a lot of our work, if not a huge fraction of it in-house, inside the United States.
I know that many of us are interested in the systems integration and systems testing portion, because a challenge that we have is that we don't have the visibility into those particular tasks. So can you expand upon the integration and the testing portions of the
Could I
rover?
expand on it, because you don't have a lot of insight into it. So basically what happens at the back end of the project is all the components get assembled, get built and tested as a component, and then they come together in a more system level, and that's what we call assembly test and launch operations, or ATLO, or system integration and test. That usually consists of, for this mission, it was a couple years worth of integration. We have a team of people sort of dedicated to do that. We have a policy where we like to keep people cradle to grave. This is perhaps something to think about for you guys managing projects or involved in projects, which is we find that the best way to test a system is with the people who specified it. Now, not every organization does that. Some people have very dedicated test teams. That's all they do. Their whole life is all they do is system level integration and test. We like to bring people in from the subsystems, from the component level, from the different disciplines, the people that did some of the conceptual work, the systems engineers that established the requirements. We bring the operators that are going to ultimately fly the vehicle. We try to bring all those people together into that part of the project because what we find is we're not necessarily taking a requirement and saying, okay, let's see if this voltage is X or Y, right? What we're doing is we're saying, let's see if this function works the way we thought that function could work. And requirements aren't always all that informative, in that way. You really have to have people don't always perfectly translate how they want it to work into a set of, words, especially if they're one sentence, So we don't trust requirements, I guess is one way to say it. We use what we call validation, which is the test of the function itself, as opposed to verification, which is the check of the requirement. And so that's a lot of what we do at the system level. That goes on at JPL, or this mission, it went on at JPL, like I said, for a year to a year and a half. And then we shipped it down to the Cape, and we essentially did the final assembly down at Kennedy Space Center over the final 5 months or so, put it on top of the rocket and launched it. And that's, in the interest of time, that's kind of what system integration tests.
Now that this Curiosity rover project is a success, and this project of this extensive size and budget, so how do you think this is going to shape up and encourage NASA for the future projects?
Well, right, if you look around the solar system, some of the easier missions have been done, the flybys and the limited, science missions and things like that. The agency is, and it's true for human exploration as well, right? I mean, we've done space, we've got a space station and things like that. We're really looking to go beyond Earth orbit, sometime soon here with human exploration again. And, I think having ultimately been successful with the mission, I hope, will give people a sense that the agency can do these large, complicated missions. Having said that, the federal budget is under a lot of strain right now, as you might imagine. This is part of what the government calls discretionary fund, discretionary money, and so it's not clear to me, that Congress and administrations and the agency and all the people that have to figure out how to do these programs can, in every case, certainly with robotic missions, fund these, something of this class in the real near term. But we'll see. I mean, that's part of what I'm doing right now. I'm actually involved in looking at the future Mars program mission space. And, one of the things we very much want to do is take this system that we have, it's extremely capable, and leverage off of it, and hopefully not have to get ourselves into a situation too soon where we have to spend, this kind of money. But I think the success of Curiosity is a good sign relative to what the agency and what the agency centers can do. I hope.
Yeah, Mr. Wallace, first of all, a huge fan, absolute respect for what you do and the work NASA does.
Thanks.
My question is again more towards the future outlook of these missions. Is there any scope where you can get back these heroes from Mars back to Earth?
Is there any way to get the rovers back from Mars to Earth? No, we don't think so. Maybe our great-grandchildren at some point will pick them up and bring them back, but they're not designed to be brought back to Earth. However, one of the most important science objectives that has been identified for Mars is to bring a sample back to the Earth, a sample of Mars back to the Earth. In part because we can't take, a room full of instruments to Mars, and that's the type of things that we need to perhaps to prove definitively, in fact, that there was at one point life or microbial life, or is life on Mars now. And so there is an interest in trying to figure out how to find a sample and bring it back. And so we're looking at ways of doing that, and looking at taking along a rocket with us, actually a Mars Ascent Vehicle, putting a sample in it, launching it into the Mars orbit, then an orbiter comes along, rendezvous, grabs the sample, brings it back to Earth. Actually, one of the concepts we have is to bring it back to essentially near Earth, and then the astronauts go and pick it up from there and bring it the rest of the way. It's a nice way to tie the human exploration and the robotic systems together. So we're looking at those types of concepts, but the rovers themselves are there to stay, I think. Yeah.
Okay, so this side. Take the opportunity to thank you very much for
Sure.
the generosity of your time,
No problem.
coming and spending it with us. It's
Yeah.
been phenomenal.
So,
With that, I know that Vishnu wanted to make a presentation on behalf of the class.
oh, thanks.
So first of all, on behalf of the class, I would like to thank you. And this presentation really shed light on a lot of unknowns that we were scratching our heads trying to figure out how that was happening.
Okay.
So we have a little something that's expressing our gratitude.
Oh, that's terrific. That's all the signatures from the class. Thank you very much. Appreciate it. Thank you all.